Hello, and a big thank you to the Scotsoft team for letting us get involved in today's event. I'm James McMinn. I work on platform and intelligence for Lumen at Bellrock Technology, and our focus is on helping organizations build and deploy data science projects. So I started building and deploying real-time machine learning models as part of my PhD way back in 2012 when I was working on real-time algorithms for detecting newsworthy events in social media. Today, I want to take you on a bit of a journey and talk about deploying data science into production. So I'll talk about some of the things that I've learned over the years, what I think the key challenges are, and describe some of the solutions that we've found help get data science into production. So I want to start by first talking about what data science actually is. Forget about the models and the maths and consider it simply as an attempt to answer a business need by looking at data. Now, I come from a background in academia, specifically information retrieval, so I generally tend to think of it as an information need rather than a business need, but really they're relatively the same thing. The issue with just talking about data and models and maths is that by themselves, they don't necessarily lead directly to value. Data science is about a means to an end, and it can help you understand something, but only if you can get information out of it. So until you've deployed a data science model, you're probably not getting much value from it. I think something else to keep in mind is that actually people doing data science don't usually have the term data science in their job title or job description. A lot of people doing data science have backgrounds in maths, statistics, physics, and engineering, and they're probably already using data to try and answer some business needs or to help with some aspect of their job. So even if you don't have a data science team or haven't specifically hired a data scientist, it's likely that you still have someone doing data science. Now, if you've never deployed a data science project before, then your current data science process probably looks something like this. You have an information need, you gather some data and spend some time cleaning it, you extract some features, then you feed that into a model, you perform an evaluation and find out how well it works. Now, you'll probably repeat this process a few times and eventually produce a report. It might be a PDF, it might be a Word document, it might be an Excel spreadsheet. But the idea is that this report gives some insight into the original information need. This is what I would call a one-off data science project, where it will only ever be run on the data scientist laptop. And once the report has been generated, the model's forgotten about. And that is fine in some situations. But actually, if you've invested in creating a model, you can increase your return on investment by deploying that model somewhere it can be run again and again on fresh data. So a one-off data science project might turn into, say, a batch project that runs at frequent intervals on their most recent data and allows a business to make better business decisions based on data that's more recent and more relevant. Now, the next step up from that is working with streaming and real-time data. So this might be a constant stream of sales data, it might be live sensor data, it might be current weather conditions, anything that comes in and needs process without delay. So if you're working with real-time streaming data, you're potentially making decisions based on data from the last second, and you can react incredibly quickly, and potentially with a good model, you can actually prevent issues before they occur. So we've worked with companies like SSE on projects to monitor weather conditions and make predictions about how the weather might lead to actual network failures. And that enables SSE to predictively have people and resources in place to fix an issue that might occur. So, of course, that doesn't come without difficulties, and actually the difficulty of deploying a model only really increases with the requirement for more recent data. So deploying a one-off model might mean you're running a script on a laptop, but actually when you're deploying a batch or a streaming model, then it's significantly more work and significantly more complex. So if we go back to the process graph, if we add in a deployment stage, it doesn't really look that much more complex. But in the same way that we're hiding a lot of complexity under the label model, we're also hiding a lot of complexity under the label deployment. And in fact, it's not just the deployment stage that makes deploying models into production a challenge, but because we're actually having to go back and change a lot of the steps before the deployment, there's actually a lot more that goes into moving a model into the deployment than simply deploying it. So what does actually make deployment a challenge? Well, deployment is a challenge because the act of actually deploying a new model is only the tip of the iceberg in terms of the effort required. So the first big hurdle in deploying any data science project is, unsurprisingly, the data. And this requires us to go back to the start, or potentially even before we've started to develop the model. And in contrast to a one-off approach where you're probably manually preparing the data, when it comes to actually deploying a model, this all has to be automated. Now, that's especially true for streaming and real-time data science, where information needs to be processed as soon as it's available, and you're maybe even handling thousands of requests per second. So even in a batch system, something as simple as uploading a CSV file, if you keep in mind that the person uploading the data probably isn't the same person who created the model, then that data still needs to be processed, it needs to be cleaned, it potentially needs to be verified before it can safely be fed into a model. Really though, for the most part, you're hoping to have access to live data. Maybe you'll be querying SQL databases, maybe you'll be polling HTTP APIs, or if you're lucky, maybe you're streaming data in real time from physical sensors. But this all requires engineering effort to set up, to maintain it, to secure it. And the truth is that access isn't always available. Sometimes it's not possible, but often it's a struggle to get. So before you consider trying to deploy any data science project, there are 3 questions about data that you need to ask yourself. Firstly, what data is actually available? Does the data that I need actually exist? It's absolutely possible to train a model on 6-month-old data that you collected from a bunch of spreadsheets that were sitting on people's hard drives. But if that's the only place that data exists, then and you don't have access to more recent data because the person who originally collected it has left the company, or there's some other reason why it's no longer being collected, then your model can't really provide value going forward. So make sure that the data you actually need exists, or alternatively figure out how you can record it yourself, and start thinking about that before you start to deploy a model. Similarly, just because the data is available, just because it's somewhere, doesn't mean that it's necessarily easily accessible. Again, going back to the spreadsheet example, you're more likely to find data sitting in a bunch of spreadsheets than you are in a nicely normalized SQL database. So think about how you're going to access the data. Can that process be automated? And what format is it in? What format do you need? If data is available but not in an accessible format, then you might need to consider who to approach and what cultural changes might need to happen for data to be made more accessible. So you're likely going to need to go out and get assistance from the people collecting the data, as well as software engineers, the IT teams, who maybe have to open up database access for you or set up an API that you can query to get data out of. So if teams don't share data, if it sits in silos and it stays there, and there isn't a company-wide push to make it more accessible, then you will struggle to build and extract value from models. this has to be a cultural change. It has to be led from within. And for organizations that are at the start of a data science journey, this is probably going to be one of the more difficult steps, because it involves change and a level of discipline that can be quite hard to achieve. So finally on this topic, just because data is available and accessible doesn't necessarily mean that you're going to be allowed to access it for the purpose you intend to use it for. There are all sorts of reasons that can prevent data from being used, from legal to regulatory to ethical reasons. And these are particularly important for things like personal information, but they extend into other areas as well. So what we've also found is that what you're allowed to do with data can often change depending on if a model's a once-off data science project that's running on someone's laptop, or if it's deployed onto servers in the cloud. So as an example of this, at Bellrock we work with a lot of large energy companies like EDF, who have nuclear power stations, and a lot of the information relating to these stations is export controlled. It is genuinely the sort of data that you go to prison for mishandling. So we have to be extremely careful working with this data. We have to ensure that we stick within any legal framework that governs its use. And we've also worked with things like healthcare data where the same sort of thing applies, where you've got a set of regulations that you must follow when you're dealing with that data. So be careful, make sure you're following any regulations or any legal frameworks that govern the use of data. And similarly, have an ethical framework. So this is perhaps not more important depending where you sit, but there's an ethical obligation when working with data. Just because you have access to information like race or gender doesn't mean that you want that data being used for training or inference. So just because you have access to data, just because you've got access to it, ask yourself, does it make sense to use this data? Am I allowed to use this data, and is it ethical to use it? So what I'm going to talk about now is something that is more common for organizations that are further along and are probably already making data decisions. But another common source of data is actually other models. So in my experience, given enough time, models tend to form a chain, a pipeline where the output of one model is used as the input to another. And it's great when this happens. It can be very collaborative, and when someone finds a model producing information that they can make further predictions on, you have to consider how are they going to communicate, who's going to maintain the model that I depend on, what do I do if that model stops producing the data or the output that I need. And I'll talk a little bit more about software dependencies later, but actually data dependencies, the pipeline jungle, etc., are a real risk and are one of those things that can actually very quickly get away from you. So if your model depends on another model, plan accordingly, make sure that you know what you'll do if that model disappears or changes in some way. So getting your model and data in order is only the start of what it takes to deploy a data science project. When it comes to actually deploying it, there are a huge number of things that need to be considered. Basic infrastructure questions like what servers are actually going to run the models? Are they in the cloud, or are they on premises? Are there physical restrictions to where the data can be stored and processed? Who pays for it? Who manages it? Seemingly simple things like how do you get the models there? How do you handle security of the servers and the data? These are fairly simple questions, fundamental ones, but they often don't have simple answers. And before you can start deploying models, you have to consider them all. Now, sometimes the answer might be, we don't care yet. And that's absolutely fair enough. But you have to be aware of the challenges so that in the future, if you do start to have issues around, say, scalability or security, at least you've thought about them and how to handle them. Right, so let's assume you've got your data sorted out. Your data scientist is happy with the research they've done and the model. You really want to start making more data decisions. What do you need to think about next? Well, the first question is the model in a production ready state? And what we see happening a lot is that it's nowhere near production ready. So the data scientist might have produced a model using something like a Jupyter notebook, and once they're happy with that, they'll tend to wash their hands of any responsibility, and it's passed on to some unsuspecting developer who's asked to make it production ready. I've been at the extreme end of this. I have, and I'm not exaggerating here, I have been given a spreadsheet that contained literally tens of thousands of rows simulating a process inside a nuclear reactor, and I was asked if I could convert that into something that could be deployed into production. Now, we're experienced enough that the answer to this was somehow yes, and that now runs in production. It's been very successful, but we only managed that because we've spent years building the technology behind Lumen. So we have our platform for deploying data science, which actually took away a lot of the pain of deploying it for us, but there's still no way of getting around the fact that this was an Excel spreadsheet. You unfortunately cannot deploy Excel spreadsheets straight to production. So we had to take that spreadsheet and rewrite it into Python. And having to rewrite a model isn't very efficient. We've heard stories of models that have been written originally in R, and then when it came to deploying them on a specific cloud provider that shockingly only supported Python, they proposed that it would be rewritten in Python. And, the claim there was that it would take 6 cloud and data engineers, at least a month to redo it. And that seems just absolutely insane to me. So you've had huge amounts of time and resources that are effectively thrown away. And if you do rewrite a model, then you have to contend with issues like different implementations giving different results. There's not always a clear mapping from one language to another language, and maybe there's slight differences in the libraries that are available, and what you have in production might not actually produce the same results as the research version. So now you have to monitor and potentially debug something that could be in production. Now, the other option is to have data scientists actually be responsible for creating the platform and producing production-ready versions of a model. But that's fraught with issues too. So data scientists are not software engineers. And any time that a data scientist spends fighting an API or managing a server or doing any other number of things that are not data science related, then that takes them away from solving some business need. And I don't think it's necessarily unfair to say that your average data scientist should not be in charge of managing or securing a server. And it's simply not something that data scientists have a lot of experience doing, and giving them that full responsibility is probably asking for quite a lot of trouble. So the solution then is to bring both sides together. Data scientists should be stakeholders in the process, and you should have your data scientists and your developers working more closely together and learning from each other. The aim of your developers should be to create a platform for your data scientists to more easily deploy models, and they can, while they're doing that, they can learn what it takes and to actually build data science software, what the challenges are, and while your developers are learning from your data scientists should be learning more about basic software engineering skills and how to write a more maintainable and production-ready code. Now, you don't necessarily want the two roles to completely overlap. You don't want them to merge, but there does need to be some shared skill set and some crossover for effective and efficient model deployment. So, no matter who is responsible for actually writing the code that powers the model, there is always going to be an element of dependency and versioning hell. Sounds wonderful, doesn't it? So it's very unlikely that the environment used to develop a model is the same or even necessarily similar to the deployment environment. So if you have a team of data scientists working on MacBooks, it's unlikely that your deployment environment is going to be a bunch of MacBooks in a server somewhere, realistically it's going to be a Linux machine. Now, you would think that if you're using a language like Python or R, that in theory you can run those anywhere, then this wouldn't be a problem. But it's actually something that a problem that we encounter time and time again. And the main cause for that is actually something that's been a problem in software engineering since about as long as the discipline has existed. So data scientists like to use lots of different tools, they use lots of different languages, they use lots of different libraries, and no two data scientists will have, the same development environment. So often what happens is that a slight variation in, say, the version of a library or the version of a language can have drastic effects on your ability to build and run a model. Now, it can even be as subtle as differences in default settings that cause a model to behave one way during development and a different way in production. And then on top of this, as sort of a compounding factor, as you deploy more and more models, you often find that different models require very specific versions of a library or language. And at that point, even if you're able to track which model requires which version of which library, you can find that it's actually impossible to install two versions of the same library on the same system. So at that stage, you're almost unable to deploy one of the versions of the model unless you put it on a completely separate machine. Now, going back to what I was saying earlier about data scientists learning from software engineers, there's also the problem of version control, or actually the lack of version control. I'm often quite surprised by how few data scientists use a proper version control system, and it's not uncommon to see model final v5 .py, which then raises the question, well, is v5 the final version? Is it v6? Is it v7? If that's the case, where is it? So you run into all sorts of weirdness, and it would be, I think, a massive improvement to a lot of data science workflows if version control is more commonly used. So what is the solution other than forcing data scientists to use Git properly? The most effective solution is, I think, one taken from the world of DevOps, which is to use containerization. So containers are images, almost think of them snapshots, that provide an isolated environment for software to run in. There's still a shared operating system, but things like file systems and libraries are contained within the container itself, as you might have guessed from the name. So this gives you a stable environment for the model to run in. And the most common method of doing this is using tools like Docker. So you containerize your model using Docker and you bundle it all up along with anything that it depends on, and that creates an image. Then you take that image and you can very safely and portably run it on a completely separate machine without having to worry about installing a particular set of libraries. Now, this has the wonderful benefit of also making builds reproducible. So what you get on one machine can be effectively guaranteed to give you exactly the same result on another machine. You don't need to worry too much about making sure that you've definitely installed the right versions of 20 different libraries, for example. So containerization is a fantastic tool. And once you start to bring all that data together and you start to build out a data-driven system, you can end up with large and complex data pipelines. And I've already mentioned data dependencies being a problem, but over time that can start to become really difficult to track what services or models talk to each other. And similarly to sort of software dependencies, you can often end up in data dependency hell. Now, issues often arise when a seemingly small change in one model has a knock-on effect on another model that consumes its output. And it can be very difficult to pick up on these side effects without constant monitoring. So there's also the technical challenge of actually connecting everything up. How do the models actually connect and send data to each other? A very sort of common way of doing your first deploy of a model is to wrap it up in something like Flask. So if you've got a Python model, you'll wrap it in Flask, and then that can respond to HTTP requests. But that can be really difficult to scale. It can be really difficult to manage, and it needs to be really well documented. So most data-driven platforms end up adopting some form of complex routing on top of message queues, like say Kafka or RabbitMQ, and they rely on those services to route data between models to handle things like what happens if you can't process data fast enough. And these sort of systems let you make it slightly easier to swap bits of the platform in and out, but realistically, you still have the platform as a whole still needs to be nice and modular. So the solution really is an engineering challenge. It's one of making sure that you document as much as possible, but secondly, it's just ensuring that you have a very modular system where it's possible to add, remove, connect, disconnect different components and services from each other. Security. How do you keep things safe and secure? This is something that I think is surprisingly not often talked about by data scientists, but it does actually often crop up when we're talking to management, for example. So I think the reason for that is that there's no single easy answer. I don't think there is a single solution to the problem of security. It's just something that you have to be very careful with and think very carefully about at every step. How secure your models and data will need to be depends on your exact circumstances. However, you almost certainly want to build up lots of layers of security. So, for example, at Bellrock, we use things like disk encryption, we have in database encryption, we have end-to-end encryption between services and modules. So you build layers on top of layers on top of layers. And even simple things like making sure you have credentials stored securely and not hard coding them into scripts for accessing a database, that might sound easy, but actually very common for a bit of test code to get forgotten about and put somewhere that it shouldn't be. So it's one of those things that's very easy to get wrong. But actually, the more layers of security you have, the less likely there is to be information leakage, and the less likely you are to have a security incident. So just think about it at every level. Take security into consideration and build it up in a layer by layer approach. So one other thing that I'd like to relatively quickly touch on is actually evaluation and the need to be constantly evaluating models that are in production. So if you're frequently updating many models, it can be very easy to update a model that performs very well during development but has serious issues in production and not notice that until it's too late and you've already made some bad decisions because of it. So the ability to monitor new models and perhaps even run multiple versions of the same model, do A/B testing for example, can allow you to very quickly spot issues, and only once you're happy that a new model is actually an improvement over the old one, that's when you perform the switch over and make your new model the live one. And one reason why you might want to update a model is due to model drift. So model drift occurs when the underlying properties of whatever your model is trying to predict change. This can happen naturally over time for any number of reasons. Behaviors might change, or there's some real world event that means your model is now less accurate. The problem here is that if this isn't caught early on, you can actually be making decisions based on what has become a faulty or inaccurate model. So rather than making better business decisions, you're actually making worse ones. And the solution there, as I've already mentioned, is to be constantly evaluating models in production. Every step should be evaluated. You can do things like statistical monitoring of inputs, so you can look for variances over time. And this can give you a clue that something's changed, but it won't necessarily tell you what. Or you can do things like constantly be updating training in a test set that you use to evaluate models that are already in production. But the important thing really is to realize that just because a model has made it into production does not mean that it can remain there forever. So I've covered a lot and I hope it's all made sense. Now I'd like to go back to something that I said at the very early on in the talk actually, that models don't lead to value directly. So to get value you need understanding, and that can take many forms. It could be visualizations, It could be access to data through some external APIs. Maybe it's a spreadsheet that gets fired off to your CFO. It could basically be any way that this information could be fired into your business intelligence bit of software of choice. But until you're able to get data out and you're able to see that data, that information, and gain some understanding, you're not actually getting value from it. So whatever you're doing the deployment process, you have to consider how you're actually going to extract data. What methods are going to allow you to get data out of a model and into some form of understanding. And what you'll probably find, as we have, is that once you start to extract value from models, once you've started your data journey and you're making data decisions, then you have more questions and you need more models, and those models in turn generate more questions, and that grows and repeats. So as you deploy and start to rely more on models, something that becomes important is the ability to scale and meet the demands of the models. Now, this doesn't necessarily mean that every time you add a new model, you need to add extra resources, but it does mean being able to add extra resources when they're required. So models can consume a lot of CPU, GPU, or memory resources at times, but often the demand will change with the time of day. So at peak times, you might be using 100 times more than at quiet times. And if you're in the cloud and you have enough resources provisioned to meet the peak demand, then you're likely spending huge amounts of resources and underutilizing your resources the majority of the time, even though they're not actually always needed. So you only really have these resources to prevent things from falling over, and that's a massive waste of money and resources. Now, the solution there is an elastic deployment. So that's where you build something that's able to scale up and scale down. You're able to add in or remove resources as they're needed. Now, early on, this might be something quite simple. It might be a manual process. You might manually add some new virtual machines during working hours and then tear them down during quiet hours. But ideally, you'll want to end up using an automated solution like Kubernetes, which can be configured to handle the scaling for you. Now, Kubernetes isn't something you want to jump directly onto. Maybe you start by looking at things like serverless functions, for example. Ultimately, though, if your dependency on models grows to the stage where this is a serious problem for you, then having to scale your DevOps team up to meet the demand is something you're just going to have to deal with. And if that all sounds like it might be a bit much, well, this is where I spend a bit of time plugging what we've been working on at Bellrock and mention Lumen, which is the platform we built that handles a lot of the complexity of deploying models for you. So we have everything from onboarding tools to ways of ingesting data to automatic containerization. We help handle things like the pipeline jungle and have a number of ways of creating dashboards and visualizations and getting data out of the models and into whatever business intelligence software you use. So no matter where you are along your data science journey, if you want to discuss something specific, or you'd like to find out how Lumen can help you make better data decisions, then please do get in touch. And with that, I would like to say thank you very much for listening. I hope the talk has been interesting and useful. Thanks again, and enjoy the rest of your day.